Okay, we're going to look at investigating data with scatter plots. Now, a scatter plot is a graph of points on a number plane. And each point represents the values of the two different variables called bivariate data. So let's have a look at what that means with the first example. So we've got the heights and arm spans of a group of students shown in the table below. So the height is one variable and the arm span is another variable. So when they're talking about two different variables, height is one and arm span is another variable. And you could think of these typically as your x values and here as your y values, right? But this time we're looking at height and arm span in centimeters. Now, when you're plotting two variables on a number plane, we call this bivariate data. Okay, bi means two, variable, so two variable data. Okay, so if you look at the first pair, we've got a student with a height of 162 and an arm span of 158. So if we go down to the graph here, that's here where the arrow is. So you can see here that student has a height of 162 and an arm span of 158. So that's the first highlighted point. If we go to the second point, which is 182, 185, that's just here. There we go. So that's 182, as you can see there, and then 185 for the arm span. Okay, so each dot represents a student. Now, we've got to describe the pattern of the points as linear or nonlinear. Now, linear means straight, and nonlinear means curved, something like this. So the best thing we can do is try and look at what sort of pattern these follow. We're not joining the dots, by the way, but if we get a line, let's change colors. If we get a line here and try and draw a line so that starting from the first point, so that roughly half the points are above, half the points are below. Let's just say 5, 6, yeah, so that's about right. Estimate. So those points basically follow that path of the straight line. So we'd say that the pattern of the points is linear. We'll put that down as a linear. Those points follow a linear pattern. Okay, now to describe the relationship, this is part B, the relationship between the height and the arm span. Well, it looks like as the height increases, here we go, the height, it looks also like the arm span also increases, doesn't it? And you can see that from the points. As the height gets bigger, so does the arm span as well. Okay, so let's write that down. As heights increase, arm span increases. Okay, so as heights increase, arm span increases. Okay, so just write that down. As height increases, arm span increases. Okay. Now another thing you should notice, just from this text box here, it says if you don't start the scale at 0, then you can use a zigzag. So you can see here we started at 140, and that's why this area here we've started with the zigzag to show that the scale is not starting at 0. We're starting at 140 instead. Now, scatter plots, what are they useful for? They're useful for visualizing and investigating. Should be visualizing and investigating the strength of the relationship between two types of quantitative variables. Quantitative just means quantity. Variables is like the height and the arm span. Now, as we said before, data sets involving two types of variables are called bivariate data. So because this data involves height an arm span. It's two different variables. We call it bivariate data. And when we're looking at the strength of the relationship, we're talking about, for example, how close these points are to the straight line that we drew on the axes. Are they all very close to the straight line or a bit further away? So the closer they are to a straight line, then the relationship is stronger. The further the points are away, then the relationship's not so strong. So let's now have a look at correlation. Correlation is the strength of the relationship between the variables and also the direction of the relationship between the two variables, and that's called correlation. Correlation is strength and direction. So now when determining the direction of the relationship, we draw a line of best fit. This is a straight line that has approximately half the points above the line and half the points below. So if we just grab a line here, and you can see if I draw the line, I've maybe got half the points above and half the points below. That's my line of best fit. If I do it again, I draw my line down here, and roughly half the points above, half the points are below. This is called my line of best fit. So I use this to determine the direction and strength of the relationship. So you can see I've basically got half the points above, half the points below. So that line is called a line of best fit. So you draw it so you've got roughly half the points above and below the line. Line of best fit. Now, if the line of best fit has a positive gradient, a positive gradient means the line goes up from left to right. We say the correlation is positive. If the line of best fit has a negative gradient goes down, we say the correlation is negative. Now, there are three parts to describing the relationship. The first one is there a relationship? Well, even though we drew a line of best fit here, you can see most of the points are nowhere near the line. So this is no correlation. Here, most of the points are near the line that we drew. And so we say that's a strong correlation. Here, most of the points are near the line that we drew, but they're not as close as in this one. So we'd say the correlation is weaker. I'd probably say actually that this one here is a medium correlation. All right, now what about the direction of the relationship? We talked about that before. If your line of best fit goes down from left to right, that is a negative correlation. And if your line of best fit goes up from left to right, we call that a positive correlation. And lastly, if your line of best fit, if the points lie very close to the line or near the line, we call that a linear correlation. But if the points don't really follow a straight line, we call that nonlinear. Let's have a look at our first example. We have to describe the correlation between students' heights and arm spans for these. Well, actually, we already did that, didn't we? So this question actually relates to, actually, no, we haven't. If we go back here to the first one, the correlation between the heights and the arm spans. That's a pretty decent correlation. We can say that definitely the correlation is positive because the line of best fit is going up. Okay, so but it's sort of weak because they're not exactly close to the line. So for the first example we did on page 1, we'd say it's positive correlation, and we'd also say it is weak. Positive and weak correlation. Now, what about this one here? Think of your straight line. If I draw a straight line with half the points above and below, that's positive. And weak. This one here, all the points are very close to lying on a straight line. get that line up a bit straighter there. So if we look at the line here, there we go. So that's actually a strong correlation because they're all so close to the line or on the line. And we would call this a negative one because the line goes down from left to right. Now, I'll draw my line here, but actually no correlation here. No correlation. The points are too far away from the line of best fit. Okay, let's have a look at another line of best fit. So we'll try and draw that there. Now, this is a negative correlation. And it is reasonably strong because they're quite close. Negative and strong. Now the next one, well, these points you'd say are strong. It's positive because it goes up from left to right, so positive, strong, right? Now you could also say that this is actually perfect correlation, isn't it? Perfect linear correlation because they all lie in a straight line, exactly on the line. So perfect positive correlation. Now for the next one, our line of best fit is going to be going down from left to right. We've got roughly half the points above and below. So this is negative because the line's going down. It's got a negative gradient. And it's reasonably weak. So negative and weak correlation. Okay, let's have a look at the next example. Now, this time we're looking at heights and handspan rather than heights and arm span. Now we're looking at handspan. Now, your job is to plot this data onto the number plane below. So the first point you're going to plot is 168 and 20. So you're going to think of this as the x-axis and this is the y-axis. So the numbers that you should put on your axes, well, you're going to start at 150 here. So start exactly where I've started. So that's 150 there. And we're going to go up by 2s. So that's 152 there. And then 154. But we're only going to write the numbers every 4 units, so it's less crowded. Okay? So just skip 1 and then you write the next number. So it's 150, 154, 158. But actually you're going up by 2s, aren't you? If you look at it, that's 156 there. Now on the vertical axis, you can start at 0 here. So 2, 4, 6, going up by 2s there. Okay? So, alright, so one of the points you're going to put is 168.20. So if we go to 168 on the horizontal axis, which is here, whoops, just here, there's 168, and then here's 20. So there's the first point you're going to plot. So your job is to plot the points from the table on that number plane and make sure you've numbered the axes the same way that I have. Right, once you do that, you've got to describe the pattern of the plotted points. Okay, so the pattern of the plotted points, that means is it linear, for example? Okay, is it a linear pattern? All right, so if we get our line tool, let's have a look. I'll just change to green. Right, so if we get a line tool, let's let's maybe start from the first point there. Try to get roughly half above and half below, maybe about there. There's a bit of a guesstimation there, but that'll do. You can see basically it follows a linear pattern. So I'm going to put linear there. Linear pattern. And then it says describe the relationship between the students' heights and their arm spans. Actually, just for part B, we should go better than that. Linear is positive relationship or positive correlation. and probably a little bit weak there. Okay, just from the data. So we could say from the data that in words, as the heights increase, the handspan increase. As heights increase, hand spans increase. Okay. All right, let's have a look at dependent and independent variables. So now if a variable y depends on the value of the variable x, y is called the dependent variable. So typically, let's have a look at an equation. Y equals 3x plus 1. I've just made that equation up. Now, to get the y value, you need to substitute an x value in there, then times by 3 and plus 1. So because the y values depend on what we substitute for the x values, we say that y depends on x. Okay, so y will be the dependent variable. Okay, y is dependent. So you can think of it as if the pronumeral is by itself out the front, then it's dependent. The x, well, we choose what value we want to put in for the x. So x is independent. It doesn't depend on y. Okay. Now, in the real world, we're not looking at x and y. We're looking at, say, heights and stride length, for example. So, for example, stride length, which is the length of a person's walking step or pace, depends on the person's height, doesn't it? Because the taller you are, the bigger your stride length. Okay, so we would say stride length depends on the person's height. So that means down here, stride length is the dependent variable and the height is independent. Okay, because your stride length depends on how tall you are. And here it says, part A, explain why stride length is the dependent variable. Well, it's because the taller you are, the longer your stride. So that's the reason. Okay. Now let's have a look at something called causality. It is important to note that even if bivariate data does form a pattern, we can't always conclude that there is a relationship between the two variables. That means we can't assume causality. We can't assume that one variable influences the other variable. So for example, if we examined a scatter plot of left foot size versus right foot size, we would see a pattern closely approximating a straight line. Okay, so if you looked at left foot versus right foot, you would see something like this. Very strong linear relationship. However, you can't conclude that the left foot influences the right foot or vice versa. The size of your right foot does not influence the size of your left foot or vice versa. So even though there's a strong correlation, one does not cause the other. Okay. Whereas back here, we could say that there is a causal relationship between height and stride length, because we know that the taller you are, the longer your stride length. So yes, we could say that your height does cause your stride length to increase. Okay, so, but not all the time. So even though it could be a strong relationship on the graph, it doesn't mean that one influences the other. It could just be a coincidence. Now let's have a look at a line of best fit now. We've had a bit of practice looking at what that is, so we're going to practice drawing this now. So in completing a scatter plot, the data may approximate a straight line. In this case, we draw a straight line as close to as many points as possible. This is called a line of fit or line of best fit. Now, how do you draw one of these? Well, the line goes through as many points as possible. The line has roughly half of the points above and half the points below it. And it is drawn so that the distances between each point and the line are as short as possible. Okay. Now the equation of the line of best fit is in this form: y equals mx plus b. M is the gradient and b is the y-intercept. Okay, so here we've got a whole lot of points, heights and masses, and we've plotted these as a scatter plot here. Your job is to draw a line of best fit. So you've got to get your ruler out for this, and when you get your ruler, you're going to try and get as many points close to the line as possible. So let's have a look. So we start from the first point here, and now you could join it to the last point, but we want roughly half above and half below. So if I did it this way, I've got 3 below but too many above. Okay, so if I move that a little bit up here, now let's see how many points are above and below. I've got 1, 2, there's 4 there, 1, 2, 3, 4 there. So I've got 4 below and 4 above. Actually, no, 1, 2, 5 there. So I've got approximately half above and half below. So that'd be good enough. So you're going to have to line up your ruler and try and draw your line so you've got half the points above and half the points below. So there's your line of best fit. Now, last thing is interpolation and extrapolation. So now this always involves your line of best fit. Okay, so a line of best fit can be used to predict what might happen. That's what its main use is. So between the points on the scatter plot, within the range of the data, this is called interpolation, right? And beyond the points on the scatter plot, outside the range of the data, this is called extrapolation. Right, this will make more sense when we come down here and have a look. So here we've got a scatter plot of arm spans versus right foot size, and you can see the line of best fit has been drawn for you. Now, part A says use the graph to interpolate the foot size of a Year 10 student with an arm span of 185 centimetres. So what we've got to do now is go to 185 centimetres. So you grab your ruler, if you like, and we're going to go to 185. So that's roughly right about here. Oh, I've got the highlighter tool on. I'll just change that to green. Let's try that again. So we're going to go from 185 up to the line. Okay, and then we're going to go across from there to see what value corresponds to that. Across from there, we've got maybe, looks about 28. Yes, that's about 28. So 28 for the right foot size. Now, interpolation means that we've read a value off the line of best fit. Here's the line of best fit point there. And that point that I've colored in green is between points on the line. It's within the scatter plot. Okay, so any value you read from the line of best fit, which is between the last point and the first point, so that's the first point on the scatter plot here, and here's the last point. So any point on the red line of best fit there that you read, which is between the first and last point, that's called interpolation. Right, so the foot size of a Year 10 student who's 185 centimetres is 28 centimetres. Next question says, use the graph to extrapolate the arm span of Year 10 student with a foot size of 31 centimetres. So we're going to go to 31 now. Let's have a look at that. We'll grab our line again. So we go to 31. 31 will be around about here. Okay. And we're going to go all the way along there, a little bit high. You can see, because 31 should be halfway between the 30 and the 32 there. So if I just move that down a bit, just a little bit, that's better. All right, so that's about halfway, maybe a little bit below. So we're going to put, now where it touches the line here, so maybe it touches about there. There it is. And we'll get our line tool again and drop down and read the corresponding number off. So roughly that's going to be 192,468, about 199 centimeters. Or if you've got 200, that's fine. You might be a little bit different. So 199 centimeters, close enough. Okay. But if you've got 200, this is a bit of an estimation, so you might have got a little bit higher there on the line. So now, because this is called extrapolation. So if you read a value off the line of best fit, which is past the last point or before the first point, that's called extrapolation. Okay, so extrapolation is when you're reading a value on the line of best fit, which is beyond the last point or before the first point. That's called extrapolation. Okay. All right. Now we will leave that there. Actually, in 609, when you get onto 609, there's the line of best fit. You can plot the points from the table there, answer the questions, and the answers for that are just over here, so you can check them. Okay.